And hello, welcome everyone to this video. Okay, so today we are going to continue where we left off. So last time I was talking about this my FFT function, which I spent a lot of time trying to describe what's going on, what's the rationale for all of these code over here. So I won't be going through that again. So if you run this code on a CSV file, and the CSV file will contain time versus input and output data, you should be able to so-called perform a fast Fourier transform on it, and then you will have the Fourier transform of the input and the Fourier transform of the output. Now, what are some of the interesting things you want to so-called get from this data? Okay, one of the things, if you are looking for a transfer function, okay, so if you have an output, okay, in let's say the omega mode, it's in terms of frequency, it's been Fourier transform, and you divide it by the input. Okay, you divide it by the input, you are supposed to get this thing called the transfer function, g of omega. Or sometimes you will see this g of j omega being used. Why is there this imaginary number here? Because e to the I or e to the j omega equals to cosine j omega plus I, okay, or j sine. Alright, there's no j omega there. My bad. Cosine omega plus j sine omega. So this is the Euler's formula. This Euler's formula, so that you connect imaginary frequencies or imaginary time constants with, or imaginary exponentials with sines and cosines. This one is a basic thing. Okay, so what are we looking for here? If we are looking for a transfer function, okay, j omega or sometimes I omega is used, whatever your fancy is. Okay, all you have to do is to divide the Fourier transform of the output divide by the Fourier transform of the input. Okay, so this will be your transfer, this will be your complex gain, something like complex gain. Okay, complex gain. Okay, from this complex gain, you will be able to take a look at its magnitude, and you will be able to look at its phase. Okay, how are we supposed to get the magnitude and phase? Okay, for magnitude, we have something in MATLAB called, let's see, gain and phase of imaginary numbers, MATLAB. Just search this on Google. You'll be able to find some of this. Very easy. So there are two ways, two methods. Okay, two methods or two functions that are supposed to get you your gain, magnitude, and phase angle. So if you have a complex number and you want to find the absolute value of the complex number, you just type in this ABS function I've shown you before. So you can see complex numbers are here. Yeah, see y equals absolute 3 plus 4i, you will get the absolute number. If you want to look at the phase angle, right? You look at the phase angle. Okay, so for example, you have a complex number in exponential form here. Okay, r equals to absolute of z, which is this complex number. Z equals to ei theta, and theta is 0.5. Okay, so if you want to get theta, you just type angle of z, and you'll get the angle of z. So you'll get the angle of the complex number. Okay, so the vertical axis is the imaginary. Okay, vertical axis is imaginary, and horizontal axis will be the real number, the real part of the complex number. So you just get theta, right? Okay, so this is how you use angle, at least in MATLAB 2020 or 2021. Magnitude, you use EPS. Okay, so I'm going to go show you a simple script to get the gain and phase, okay, based on your frequency response data. So if you have a frequency data column like this, okay, a frequency response data, you have a frequency in hertz, and then you have the input frequency response, and then the output frequency response. What do? Okay, you will need to divide the output by the input, okay, and divide the output by the input. Okay, so all right. So the thing is, with this what do you call that, code, or with this arrays, you cannot just use the divide button if you want to divide the output, which I'm selecting here, by the input. So if you want to divide, you know, the input of the first row, I mean you want to divide the output of the first row by the input of the first row, the output of the second row by the input of the second row. I mean, there are two ways around it. You can actually set up a for loop to divide it number by number, and that's how you normally do it. But with MATLAB, there's a very easy syntax. You use this dot and divide, okay, dot / okay. So let's see. So let's say input equals to frequency data, all rows second column, output equals to frequency data, all rows third column, okay, gain equals to output dot divide by input. So the complex gain will be this whole this whole column over here. So if we were to plot let's see, frequency data, the first row, which is all the frequencies, and I plot it against gain, the complex gain, or maybe absolute of the gain, then I will get the following. And you can see, you know, the gains at various frequencies are as such. Okay, of course you will not be interested in most of these because those are noise, and what you'll be interested is your gain at the primary frequency, which will be somewhere around here. Okay, it's supposed to be 2 times 10 to the minus 4. I don't know where the peak is. Let's go back to home. All right. Okay, 2 times 10 to the minus 4. Okay, so this is the gain here. It seems to be so-called the lowest part of, okay, or 2 times 10 to the minus 3. At 2 times 10 to the minus 3, we have like the lowest gain here. Why is that so? Okay, if you were to take a look at the output and the input, okay, I mean, all the rest of these are noise, but you see that okay, let's see. Let me plot this for you. Okay, absolute of input. Okay, let me okay, so yeah, you see that all your input will be at this particular frequency, 2 times 10 to the minus 3. And I can zoom out and you can see the two peaks very nicely there. Not an issue. This is how it should be. Okay, you have this peak over here. Let's check the output. All right. Let me try again. All right, output equals to frequency data all and 2. Okay. All right, never mind. Let me just show you CLF first. yeah, if you look at the output, you see that the peak is also at 2 times 10 to the minus 3. Okay, now if you divide a big number by another big number, you'll get a very small number, which is what you were seeing just now. Okay, but if you were to divide so-called smaller numbers here by another small number, then you will get very widely fluctuating sort of numbers, as you were seeing here. Okay, so remember, if you take a look at 2 times 10 to the minus 3, you see that this gain is going all the way at the bottom. You see here, all the way at the bottom here. So the gain is about 0.95 or something like that at this particular frequency. Then you have all these other peaks, which they are very big because of the noise patterns in the output. Okay, you have small numbers divided by another small number, so the results can fluctuate a lot. So in fact, if you look at this graph, it's not exactly the most useful over here because of all this noise. Okay, yeah, but long story short, if you were to want let's say your gain, okay, you have your absolute of the absolute value of the output divided by the absolute value of the input. That's how you would do it. And this is the magnitude. All right, this is the magnitude. Okay, the way I did it, I didn't put the absolute when I do the division, so it's kind of a complex gain kind of a thing. Okay, so this one makes it very clear that I'm dividing one magnitude by another magnitude. Next is the angle. Okay, the angle. So I'm getting the phase for both of them. I'm using the angle function, and let's see what unit this is in. Angle output. Yeah, so these look like they are in radians because it's 1.5 minus 1.5. 1.57 is about pi by 2, so that's more or less why it's around this range. Okay, so this is in radians and this is in radians, and the phase difference will also be in radians. Yeah. Okay, so this is all that we are doing with this script. These complex numbers is to get the angle and the absolute, okay, the magnitude of these, and gain is just to divide one by the other. Phase is to subtract one of the angles from the other. So is the phase difference will be the phase angle of the output minus the phase angle of the input. That is the phase difference. This script is very simple, so yeah, it will take all this data, it will find the gain and the phase, and it will plot the absolute gain, the magnitude of the gain, and the phase difference in radians, and you'll pass it out as some sort of a function. I mean, some sort of an array. So let's just try that there. So gain and phase equals to gain and phase frequency data. That's how I'll type it out. And okay, so this one will just tell you, what are all the various gains and the various phases at each frequency. And the frequency we are more concerned with is of course based on our input frequency, which is here. Okay, oh sorry, not here. It should be 2 times 10 to the minus 3, which is here. You can see the gain is almost close to unity gain, and the phase angle shift is about minus 0.356 radians. Okay, so that's all there is to this gain and phase. If you want to find the gain and phase of your Fourier transform data, that's how you would do it. Okay, but you have to always know what your input frequencies are. So for example, if I have my input frequency at 2 times 10 to the minus 3 hertz, if I have that's my input frequency. Okay, I only want to zoom in on the input and output ratios. I want to zoom in at gain at this frequency. So I only want to find the gain at this frequency and the phase angle at this frequency if I want to do this frequency response testing, because all the rest of it is just noise. Okay, if I have multiple input frequencies, so it's a more complex thing. So maybe I have this one, which maybe is 2 times 10 to the minus 2 hertz. Then I will need to make sure to look out for the frequency 2 times 10 to the minus 2 and 2 times 10 to the minus 3, because both of these are superimposed on my input. Now I need to take a look at the gain and phase angle for them. Okay, so that's the idea behind frequency response. Normally you will just put in one sine wave, but if you want to really speed things up, you can put in multiple sine waves at once. You can do in some other signals called pseudo-random binary sequence. Okay, so some of those that will help you to speed up some of your frequency response testing. Okay, so this part is very straightforward, but it presents us the problem because like I showed you over here, if we were to plot the frequency data, all rows first column versus the absolute value of the gain, okay, we will have all this noise. So we cannot just take the data like this, lock, stock and barrel. There must be a way to so-called filter out which data is actually valid. And the way we know it's valid is if you see this, if you already know your input frequencies. Okay, if you know your input frequencies, you will know which peaks to actually look out for. And this thing doesn't really look like a peak, it's more like a valley. And all the other parts of this are just noise, so we can ignore. And that's a good thing about frequency response. You can just actually ignore all the noise and focus on the input frequencies that you are giving it, so that you can find the gain and phase. The gain and phase kind of thing. So that's what you're supposed to do. Now, how then are you supposed to do it manually? Okay, how are you supposed to do it manually? Okay, if you are doing it manually, you have to know all your input frequencies. But is there a way to automate this? Yeah. The answer is yes. Okay, the way we do it is using this this toolbox known as signal processing and communication toolbox. This will actually help you to analyze your signals. Okay, I have not used this one, but I used it in the script mode. Okay, let me show you my peak finder script. Okay, let's see this frequency data first. Okay, let's see. Well, I've not actually tried using this yet, but this will be interesting to play with. But anyway, I'll not save this. What I'll do is this over here. Okay, basically, if the trick is this, okay, the gist of the trick is this. I'll explain that and then I'll move on to the next video. Okay, the trick is this. If you notice your input, you will have certain peaks which you know are your input frequencies. If you look at your Fourier transform of the input, you know that the input here is 2 times 10 to the minus 3 hertz, because there's this big obvious peak over here. If you actually put in multiple frequencies, you can look at the Fourier transform of the input and you take a look at, okay, maybe you have multiple peaks, one at 2 times 10 to the minus 3, one at I don't know, 2 times 10 to the minus 2, 2 times 10 to the minus 1, whatever you have. I don't know what your peaks are, but you can actually look at the peaks over here. And the way you would actually tell MATLAB, hey, I want to find peaks, okay, you literally use you use the function called find peaks. Okay, find peaks. Okay, this is just to help you find local maxima. Okay, so this is what you use. This is how you use it. PKS equals to find peaks data. Okay, data is Okay, data is your input, okay, over here, input vector. It must be real and at least have 3 elements. Okay, yeah. So yeah, and this is probably what you want. Okay, specifies x as a location vector. Okay, so anyway, we can explore all of this next time. But let me demonstrate to you how this find peaks thing actually works. So what I need is a frequency data input, and it will give you some peak data as an output. Okay, and actually I do some plotting over here as well. Okay, so let's do a peak finder. Frequency data. Okay, and what will you have? Okay, you notice that we have the Fourier transforms of the input and output. Not only that, this peak finder actually puts arrows over here. Can you see? It puts arrows over here to tell you, okay, I found a peak here. And if you take a look at the output, there are some peaks as well, spaced out evenly. I did not bother identifying every single one because sometimes it's too sensitive. I didn't calibrate it so that it will find every single peak. But the idea is this, okay? At some certain threshold, you will be able to identify some of the peaks. As you can see, there's one peak here, one peak here, one peak here, and it's kind of evenly spaced at certain intervals. And then the rest is just, background noise. Do note that all of these are plotted in a decibel sort of what do you call that? Units. So that's why we have this logarithmic shape. Okay. So you can see that the Fourier transform, there's a mirror image of the left on the right here. That is a standard thing, and then the Nyquist frequency will be around 1 Hz. Okay, so the peak finder is supposed to help you find where your peaks are. That's what its name is saying. So that's what pretty much it does. Good, well done to the programmers. Okay, okay. So with this peak finders, you will be able to see where your peaks are. So for example, your input peak frequencies. Okay, if you take a look at the answer, if you take a look at the input peak frequencies, you'll see input peak frequencies will be at 2 × 10⁻³ Hz, and then somewhere slightly below 2 Hz. But you notice this frequency is of course above the Nyquist frequency, so we can just ignore. Okay, and then the output peaks are all of these. Okay, oh, this is in decibel, sorry. Output peak frequencies, okay, 2 × 10⁻³ Hz, 8 × 10⁻³ Hz, so on and so forth. So these are your output peaks. But the only thing you would bother is to compare your input and output at where your input peaks are. So I only have one input peak over here, so I will only bother to look at the input peaks over there. Alright, so this is how I would use it. Okay, next time I would how do you say? Yeah, I would show you how to use it and why I code it in a certain way. Okay, but this is a manual way. You tell peak finder to find the peaks for you, and then you kind of look at the data yourself. Okay, if I play this whole code, I look at the frequency, I look at the frequency data, gain and phase, blah blah blah. Yeah, I will get that, and then you have peak data to look at. You can check out what frequencies you must look out for. Okay. Alright, so I will see you again next time. Hopefully, yeah, we can look at how this peak finder thing works, how we can tweak it to see what we want. Okay, thanks for watching.